Okay, let me start a timer. Well, no, I'll make you guys listen as long as I'm talking. All right, so I'm going to talk about anharmonic phonon coupling and in-plane heterojunction fabrication in two-dimensional indium selenide. If you want to follow along with the slides, they're downloadable with the QR code. And if you're one of my family members, everything's going to be backwards, so you can see the slides. There's a link in the YouTube description. I want to thank my committee and all the collaborators that helped with this work, without whom none of it would have happened. Let's get started. So indium selenide is a van der Waals material, and a van der Waals material is a crystal. So the important thing here is that all of the things that are true for crystals are true for van der Waals materials, and then down to indium selenide. So crystals repeat in space, and a van der Waals material is a crystal. So you can see graphene here repeating in space with this nice hexagonal pattern forever. But what makes it a van der Waals material is that it forms these sheets, because it has covalent bonds within the sheet and only van der Waals bonds outside of the sheet. So the rest of the world, the rest of the universe, interacts with these materials via the van der Waals force, which is why we call them van der Waals materials. So the important things are that they're layered, and they have in-plane covalent bonds, and there's no electrons left over for out-of-plane bonding. And then there's a whole bunch of these materials. Graphene and MOS2 are the two most well-studied ones. And you can see their crystal structures here. But today we're going to talk about indium selenide, which is another van der Waals material that has 5 layers instead of 3. So indium selenide, the thin film, has a lot of crystal phases, but we're only going to talk about alpha and beta here. Now, the reason we talk about alpha and beta will become apparent through the discussion, but alpha and beta have a 5-layer structure with 3 layers of selenide sandwiching 2 layers of indium, and then a repeating crystal. And then they look almost exactly the same for 1 layer, but they repeat differently, as is sketched in this diagram. And you can, when you exfoliate it, you get alpha phase, and you can go to beta phase and gamma phase and kappa phase irreversibly by heating it. So if you heat it up, you get a phase change, and then it does not return to its original crystal phase when you cool it back down. So these phases are metastable, which is interesting. So very similar crystal phases, as we can see with the TEM image here, where alpha and beta have a lot of the same symmetries. And then the other thing I want to draw your attention to is that the alpha and beta phase are so similar that their in-plane crystal asymmetry in the delta A over A is less than 1%, and their out-of-plane is less than 2%, which means if you make a device, you won't have very many lattice mismatch problems. So let's go through do a very brief introduction on 2 of the main experimental techniques we're going to use. Okay. So when you shine a light into a material, it usually bounces back, and this is Raman scattering. So when you bounce light in, it comes back with the same wavelength. That's inelastic scattering, and basically, no matter where the electron starts, it's going to come back with the same energy. But very rarely it will come out with a different energy than it went in with. And because energy and momentum are conserved, that energy and momentum have to have had come from somewhere. So they come from the crystal itself, and then by probing the difference in the energy that went in versus the energy that came out, we can learn about the crystal symmetries and what bonds are allowed. So crystals are periodic in space, and they only support certain lattice vibrations. And using Raman spectroscopy, we can learn about those vibrations. And then the last one we'll talk about very quickly is photoluminescence spectroscopy, which, rather than measuring the crystal states of the crystal structure, it measures the electronic states that are supported. So you shine a light, so here's a very simple illustration at 0 temperature, where we have a fully occupied valence band and a fully empty conduction band and empty defect states in the middle. So when we shine a laser at T=1, we promote a whole bunch of the states to the conduction band, and now they want to decay down. But again, energy and momentum are conserved, so they can only decay via phonon emission, or via photon emission from the bottom of the conduction band to either the defect states or the top of the valence band. And we measure that radiation that comes back, and we can learn the energy difference between this first defect and the second defect and the band gap of the material. So now we can look at these 2 techniques for indium selenide. On the far right, we have the Raman spectra of indium selenide. alpha and beta phase. And we're going to dive into that a lot in the first or the second third of this presentation. Notice first that the full width, the width of the alpha phase is much more narrow than the beta phase. And this is telling us about the crystal, and we're going to examine what's going on there soon. Then we have a sketch of the band diagrams of these materials. They're both N-type semiconductors with band gaps where beta's band gap is much smaller than alpha's, which is quite strange because they have almost the exact same crystal. And then on the far right, we have the photoluminescence spectra, which we're going to use later. Alpha's in black, beta's in red, and the substrate that beta was on is in blue, just to show that the photoluminescence that we see from beta is not really from beta, it's from the underlying substrate. Like this band gap is 0.4 eV, and the energy range we're looking at is 1 eV to 1.6 eV, so we wouldn't see a photoluminescence peak from beta anyway. And also alpha has a direct band gap at 1.32 eV, which is what we see there. Now, this is the optical properties, but let's look at the electrical properties. And this is where we really see the difference between alpha and beta phase. Okay, these are all the same chart. They're all the same measurement within a column, and across the rows is for alpha phase and beta phase. And on the far right is the circuit diagram where all of these came from. Instead, in the first column is images of the devices that these were taken on. And what we can see in this first column is the drain current versus the drain source voltage. And what we see is that the alpha phase varies a lot as we vary the gate voltage, whereas the beta phase varies almost not at all. But what we should point out is that this scale is on milliamps and this scale is on microamps. Okay? Beta phase conducts way more electricity, even though it's not tunable. Okay, even though it's not tuned in this 40 to -40 range. So to highlight this further, we look at the second column, and what we're plotting here is a constant drain source voltage as we vary the backgate voltage. And we see that the current that passes through alpha varies over 3 orders of magnitude, whereas beta varies over like -3 orders of magnitude, but still at 1,000 times more than alpha phase. Okay. And then finally, we want to look at the resistance, and this is the real kicker because we think beta is a semiconductor, but it behaves exactly like a metal if you look at the resistance versus temperature. Alpha's resistance decreases because as you heat it, you populate the conduction band with thermal electrons, but beta phase, the resistance increases with temperature because you get more scattering events because the conduction band is fully populated to begin with. So from here on out, we're going to talk about alpha as an N-type semiconductor and beta as an N-type semi-metal, and I'm probably just going to say metal. Okay, so that's the electrical properties. Let's motivate the first portion of this work. So in 2017, Xiaoming and colleagues, Wang et al., they made an alpha-beta device. You have a metal and a semiconductor, so you want to see if it makes a good junction. So they had beta phase indium selenide, and they exfoliated on top of that alpha phase indium selenide. Okay, and it had a whole bunch of very interesting properties, ideal diode behavior. But the most interesting one, the one that motivates this work, is here on the right, or on the left. So we have the photocurrent as we raster the laser over the sample. We measure the photocurrent in each spot, and then on the left is on the right is the reflectivity as that corresponds to the photocurrent. What we see, interestingly, is that the short circuit photocurrent, so there's no bias applied anywhere, the photocurrent goes from beta to alpha, which is the opposite of what you would expect given the photovoltaic effect. And Xiaoming and Wang et al. Showed that it was because of the photothermal effect, where you were heating the carriers and they were moving. So that effect overcame the photoelectric effect because they point in different directions. So they ended up showing that this junction has a figure of merit about 1, and this is just a way to count how many electrons you get for how many photons you throw in, or how much the heat difference across the material. How many electrons do you get? Anything, if you heat one side, you'll get electrons out the other side, but the thermoelectric figure of merit would be bad. And then being approximately 1 is really cool. That's right at the edge of what is industrially useful, and the world record is 2. Okay. And the most interesting thing here is that alpha and beta phase on their own are both terrible thermoelectrics. So here we have a factor of about 1,000 increase in the thermoelectric efficiency by stacking them up. And we wanted to figure out what was going on there. So in order to do that, we needed to know the thermal properties of alpha and beta phase. So let's figure it out. All right, so the first thing we're going to do is look at the Raman spectra as a function of temperature, because what that tells us is the underlying crystal dynamics. And we expect that when you heat it, that will show up in phonons, which are crystal vibrations. So what we have here is a model from IN2SE3 et al. That shows that we can split this gamma term is the full width half maximum of these Raman peaks. We can split it into a phonon impurity term and then an anharmonic term. Okay. And then we want to figure out what this anharmonic term is with this n omega t is the Bose-Einstein distribution for each phonon. So then we have to figure out, well, here's our 109 or our 105 peak in alpha and our 109 peak in beta. So there's DFT calculations for what the phonons are going to be. And the only way to get to 105 is to take 80 and add 20. So we have a 2 phonon process for this. Do the same calculation here, and we get 3 phonons that add together for this peak. So now
just a clarification. Yeah. For the 105, 109 peak, are you saying that is a K equals 0 phonon?
Yeah.
And then when you're adding up, that's what it decays into?
Yes.
Okay.
Yeah. And the Raman spectra for beta is much weaker than alpha, which supports the idea that it's going to be more phonons involved. It's less likely to happen. Since the lion's share of this problem was actually a curve fitting exercise, let's go through the specifics. Sketch this. I'm not gonna see any code, but we'll give you the idea of what happened. So the problem is that alpha has a very easy to fit peak, right? Nice and thin, isolated, easy done. We want to check the full width half maximum. We know that the peak underlying it is a void peak, which easy enough to fit. The problem with beta is that at very low temperatures, you get 2 peaks, but as you heat it up, these peaks collide with each other, and they move closer together, and their full width half maximums increase. And at about 160 K, you get a third peak that's off on the side that's very broad, and that very broad peak starts to spill into these other 2 and makes them indistinguishable. Now, if you had an infinite data sampling, it wouldn't be a problem. You would deconvolute the 3 peaks and wouldn't be a problem. But in the real world, we have a lot of noise to deal with. So we have noise and then sparse data sampling. There's not really a way to get around that. So if you have to fit a noisy peak, you need to be very careful with the initial parameters. So the first step is to use the previous peaks, the previous peak location, and extrapolate them forward for your initial guess. Okay, so that you start with an initial guess that's at least close to where you want to finish. Otherwise, your peak won't converge robustly. And then the second thing we did, because we couldn't deconvolute these peaks, there's not enough data. We had to do an analog version of deconvolution where we see the blue is the data, and then the green is less than 110 inverse centimeters. The data is almost entirely this first peak. So what we would do is fit the data from say from 90 inverse centimeters to 110 with the left peak, and then subtract that from the total spectra, and then fit the right peak. And then we would subtract the right peak from the total spectra and refit the left peak. And we would continue doing this until either the peak didn't converge or it converged. And then there was a bunch of fairly robust ways to determine if it converged or not. And we would, by varying different parameters in different orders, make sure that you're not finding a fake peak. So now we have the full width half maximums for the 2, and that's what we're looking at here. And we'll note that even with all this clever nonsense, the beta phase is not extractable beyond a certain point. These last 3 peaks you only get with all the clever stuff. The first 3 are easy to fit. So without those next 3, you couldn't draw a trend line and figure out what's going on. But now we have the full width half maximum, and we can determine what that means for this crystal. So we curve fit these to our model, and what we get is the gamma knot term, which is less interesting. We fit that. But this A term, the anharmonic coupling term, is what we want to focus on. So the anharmonic coupling term for beta is about 3 times what it is for alpha. And what that means is that we expect the anharmonic phonon processes to be more dominant in beta than in alpha. So, but this doesn't answer our original question. Our original question was to try to figure out what are the thermal properties. This is a useful hint, but we need to keep going. So in order to figure out the thermal properties, the thermal transport of, or the thermal conductivity of this alpha and beta phase, what we did was we exfoliated the alpha phase over a hole, or the beta phase over the hole, because there's very weak coupling between air and indium selenide, and a much stronger coupling relatively between indium selenide and the substrate silicon nitride. So then we shoot the center of it with a laser, and then we measure the Raman peak that we get back, and now we have a partial differential equation to solve, right? We have heat coming in, we have a temperature raise, and we have heat going out. So it's not a solvable analytically problem, but with finite element methods, we can solve it. We're not going to talk much about that because that was work done by a colleague, but we use finite element to solve the differential equations that we can't. And then here's a picture of the experimental apparatus, or the experiment actually set up, where we have, in this case, alpha phase exfoliated over a hole. So then the important parameters that the computer is going to need is the peak shift versus laser power that goes in. That's going to tell it how much heat. And then we need the peak shift versus ambient temperature to figure out how much the temperature increased. And then we can do numerical simulations for the heat dissipation. So that's what we see here. And let's focus on the left side first. So what we see here is this is for alpha phase at 105 Kelvin. Now, what we see is the peak position versus the incident laser power. So as we shoot the laser at it more, the peak is going to move, and that is going to be due to the heating of the crystal. Now we can fit this, and what we see in this inset is the slope of this line at different temperatures for alpha phase. Okay, it's a similar picture for beta phase. So we have this, but in order to figure out how much, so now we know how the peak moves with power, but what we want is how the peak moves with, or how the temperature changes with power. So we need to measure how the temperature moves, or how the peak moves with temperature. So for this one, we did a slightly different experiment where we put the indium selenide on the substrate without a hole because we wanted there to be no heating. And then we used a very low laser power and a very long integration time to keep it from heating. And we made sure that there was no laser heating going on in this experiment. And we can extract this line, which is the amount that the laser peak will move as a function of ambient temperature. And now if we take the ratio of these two numbers, we have how much does the peak move as a function, or how much does the temperature change as a function of power. That's what the software needs to solve the heat equations. So now we have that, and it's the software is going to dump out a thermal transport parameter. But we want to figure out what's going on here. Okay. In order to do that, we use the Callaway model from a guy named Joseph Callaway in 1954. And the heart of this model is this relaxation term. Okay. You see this the heat transfer as a function of temperature. There's going to be a whole bunch of constants here: temperature, the Debye temperature, and then the relaxation term. Okay. And this relaxation term, the model is to break the relaxation into different components. Okay. So the first component is Phonon boundary processes, where we intentionally made our layers very thick so that didn't matter, and then we simulated it with different thicknesses and it didn't come up. So we can kind of ignore this term. And then we have phonon impurity scattering and phonon umklapp processes, right? Now, impurity scattering is relatively easy to explain, right? You have an infinite crystal, except it's got an impurity in it. So now you have a phonon coming along, sees that impurity and scatters off of it. Umklapp process, let me explain in the next slide and then we'll come back. Okay. Umklapp is one of my favorite words in all of physics, because if you know what the word means, you know what's going on. Unlike, most things are named after somebody's name. Umklapp means to fold over, which is exactly what we do. So in an infinite periodic potential, you can't leave. because if the universe is more than our unit cell, it doesn't work. So in order to maintain, you have a scattering event that kicks you out of the unit cell. In order to get you back in the unit cell, we say, well, you came in the other side, right? Can't leave. And that means, the German word means to fold over, which is exactly what we did here. Now, this nifty trick, there's some consequences though, right? One is that for phonon, for scattering process to occur at all, you must have an anharmonic potential. Otherwise, the superposition principle is true and waves cannot scatter. So, one. Two, momentum is not conserved, and that's now we have a term that we call crystal momentum. That is conserved, but we had to give up momentum conservation, which means that we must do this in order for momentum conservation is like the sacred cow of physics. If we gave that up, we had to get something in return. And what we get in return is that we can explain transfer processes, heat transfer, and basically anything that tries to leave the unit cell. All right, so that in mind, we come back to our model, and we do the curve fit on these heat transfer coefficients that were from the finite element analysis. And what we see is that we have these parameters, okay? Alpha, or A, B, and then A and B. And numbers are kind of meaningless on their own, but relative to one another, they can be meaningful. So what I'll point out first is that this B term, the Umklapp process, is about 5 times stronger in beta, okay? So it is more of the transport limiting mechanism in beta than it is in alpha. And then the other thing I will point out is that this A is 10 to the negative 48, where B is 10 to the negative 19 or 18. So relatively, the Umklapp process dominates the impurity scattering process. And then we show that by this inset, where we fit the same equation to our data, except we only put in the Umklapp term, and we get back basically the fit. And then we use only the phonon impurity term, and there is no fit. Right? That's not the dominant process in this reaction. So we've shown what the thermal transport limiting mechanisms are in alpha and beta. But the very interesting thing that we should focus on here, right? Alpha having a low transport is not weird. It's a semiconductor. It's not going to be that great at transferring heat. Beta having a very low thermal transport is strange because it behaves as a metal electrically, but it behaves as an insulator thermally. That's why it made such a good thermoelectric material before. The heat couldn't leave. So you could heat up an area locally, the electrons can leave, the heat can't. All right, so that's the end of project 1. Everybody take a breath. I'm gonna get some coffee. Get going. All right, so now to introduce the ideas for the second project I'm going to talk about. We need to talk about how heterojunctions work, right? So here we have a band gap of a bunch of transition metal dichalcidides, and then different conduction band or different band alignments that can happen in semiconductors. Now, what I want to focus on is this far column. So if you have a sheet of paper, right? There's multiple ways to stack sheets of paper, but there's basically only 2, right? You can stack sheets of paper this way, or you can make them touch on the edges. And that's the difference in these heterojunctions. So you have vertical heterojunctions, which you stack them on top of each other. And then you have lateral heterojunctions where you get them to butt up against each other. Most of the work so far has been done in vertical heterojunctions because it's a much easier way to do research. Basically, you give your grad student a microscope and that's all they need. It's a microscope and some tape, and you can mechanically stack layers ad infinitum. And it's very cheap because grad student labor costs nothing. but it's never going to be scalable, right? It takes one grad student 1 hour to make one device. You're never making a computer chip, right? So a lot of focus has been put on growth methods. And the idea here is that we would either grow a vertical or a lateral junction. So this paper, what they grew was MOS2 in the center and then WS2 on the outside. And the specifics of those don't matter. What matters is that they grew a heterojunction, right? That was in plane. There's a lot of problems with this, right? Crystal growth is a difficult thing on its own. Controlling nucleation sites is difficult. Getting the bands, getting the crystal structures to align is going to be difficult. So there's a lot of problems to overcome in these methods. So what we wanted to do was to have one growth step and then a patterning step, right? So if you grew an entire sheet that was uniform and then made it selectively non-uniform, and that's what we have done. So we have a material that we've been talking about this whole time that is a semiconductor in one phase and a metal in another, and you get from one to the other by heating or by pressure. And what we wanted to do was try to locally heat it to cause a phase change. So let's look at what other people have done in this field, because we're going to use a similar method. So in 2017, Kim et al., they were the first ones to use laser thinning on MOTE2. And what they did was they had a 21 layer thick stack of this material. And then they shot it with a very high power laser and basically evaporated the surface until it was thin enough that these last couple of layers were sufficiently bonded to the substrate that they wouldn't evaporate anymore. They could dump heat faster than the laser could put it in, and they quit evaporating. So sure enough, here's their 21 layer stack, an IV curve. It's a resistor. Their 4 layer stack is not a resistor, but it's also not a very good device. And that's why we want to keep working, right? There's not very good rectification here. You get negative 10 at 1 volt, or negative a volt, and 10 at positive a volt. So there's still work to be done, and that was done by Sao et al. And what they did was they CVD grew a big strip of MOTE2 and then patterned gold electrodes on top of it. Then they used a laser to heat the gold. So this is a cartoon on top of an SEM image, and this is just a cartoon showing what's going on. But that laser heating caused local P doping via, they evaporated some of the molecules, so some of the atoms, and you got P doping. And what you can see here is that they got a very good device where from 1 to 2 are the electrodes that have been heated. So there's P doping between them, and the carrier concentration drops dramatically. You get less current flowing. And then 3 to 4 were unmolested, so they have the regular MOTE2 properties. But when you go from 2 to 3, you see a lot of rectifying behavior. And that's a good indication that you made a nice PN junction. The last thing they did, which is very cool, is they grew a bunch of circles and then patterned the electrodes on this way to make solar cells, because now the junction is wide, and they're able to achieve 16% efficient solar cells on their first time with this technique. So we wanted to try to apply this technique to indium selenide. First time we got it to work was 2017, but now if you can't do it reliably, it's not science. So this is how we finally got it to work. So we have an indium selenide layer, alpha phase, and we put HBN on top of it. Then we heat this this combination to about 100 degrees less than the transition temperature. Okay. Now it's 100 degrees less than the transition temperature. Transition won't happen. Then we shoot it with the laser. So first we measure the phase with a very soft laser. Measure the phase, and that's what you're seeing here, alpha phase. And then we shoot it with a very intense laser, or not even very intense, 3 milliwatts, right? We shoot it with a laser, and then we measure the phase again, and now it's beta phase, okay? And we had a lot of question of whether it would be stable at room temperature, right? Because now you have lattice mismatch, right? You have a beta phase buried inside of an alpha phase, and when you bring it back down to temperature, it might not be stable, right? It was, which is great. So then we could peel off the HBN, we place gold electrodes or indium gold electrodes so that the work functions work out. And now we have a device. Right? So the first thing we did was to try to do this reproducibly. And that's what you see here, where we took alpha phase crystal and then just made it look like a leopard. Just it's got polka dots of beta all over the place. We wanted to make sure we weren't burning holes in the sample, and we wanted to make sure that these were stable. So, both is true. So this little white box is the AFM profile and the KPFM profile, okay? And what we see in the AFM profile is a smooth topography over the interface, which is exactly what we would want. And then what we see in the KPFM profile is not a smooth work function, okay? And then we have the traces here, and these traces are taken across the fat part of this oval, okay? Where we have alpha phase over here, beta phase in the middle, and alpha phase. So on the one side, we see the work function difference of about 300 millivolts, 250, and then the topography is smooth, and that is good, okay? Then the last thing we wanted to check is to see if we preserve the single crystallinity of the indium selenide. So in the past, we've shown that the alpha phase to beta phase does not change the orientation in plane. So that's what we're checking here with the exact same setup, but we exfoliated over a TEM membrane, and then put the polka dots in it. And Matthew did a TEM, and sure enough, we have the same crystallinity for the alpha and the beta phase. All right, so if we can put a bunch of polka dots, that's nifty, but what we want to do is make a device. So that was the next thing we did. And the idea here was that we took a whole bunch of these polka dots and just joined them together, hoping if we do that, then we'll have a beta phase region and an alpha phase region. Okay, so here's the device on the left, a KPFM map, and then a KPFM AFM trace of this dashed line. Okay, and yep, don't see any crazy holes. We see one crazy hole because a little too much laser power, but we have fine device properties. And then what I'll bring your attention to here is that basically wherever we draw this line, we get the same smooth topography, same work function difference, but a 500 nanometer alpha to beta transition region in the work function. Okay, and this was true on all the polka dots we drew, on all the devices we made, and I think we're at a dozen or so now. So we have a 500 nanometer junction, and then a 300 millivolt change in the work function. All right, and smooth topography. All of this is cool, but the point is to make a device. So we have work function mapping. Let's make sure that everything works with optical imaging. So that's what we see here. Same optical image. Then we have a schematic of the scanning setup for the photoluminescence, and then again the photoluminescence for reference. And what we see here is the counts, which is just we do an integral over the fat part of this alpha peak, so that we can see the difference between alpha and beta. Right, beta is almost zero, alpha is non-zero. So we should be able to see alpha integrates to something greater than zero, beta integrates to zero. And sure enough, this agrees with the KPFM mapping. And if you have two measurements that say the same thing that work on different processes, you can be pretty sure that what you have is real. And then what we have at the bottom here is a different measurement. So this is a short circuit photocurrent map. And this is an interesting, predicted thing. What we did here, rather than scanning the sample under the laser, we have tuning mirrors that move the laser over the sample. But what we see is that we have a large photocurrent well away from the junction. The transition region on the junction is 500 nanometers here. Now we're multiple microns away and we're still seeing a strong photocurrent. What that means, and at zero bias, what that means is when you're promoting an electron from the valence to the conduction band, it still gets a net momentum from somewhere. If there's no net momentum, then it would go to each side equally. You won't see a net photocurrent. So this net momentum, we think, and like previous theory papers have suggested, is because these devices are so thin that there's a large fringe field, right? A dipole cannot screen. If you solve the E&M for a dipole, you get an electric field everywhere. But if you solve Maxwell's equations for a parallel plate capacitor, you get a very localized electric field. So the idea is that since there's so much fringe field, an electron anywhere in the material will feel a force. And I think, and we're going to keep working on it, but it seems to indicate that. But let's see what the actual device performance is. And this is where we get weird. Okay. So a regular diode will pass almost no current when it's negatively biased and pass a lot of current when it's positively biased. And there's a turn on point about 0.7. Which is not what we see here. And first time we did this, we thought, okay, bad device. So make a bunch more. And when we didn't get a different answer, we say either they're all bad devices or there's something interesting here. So first thing we do is we make a semi-log plot of the positive voltage. And what we see here is a straight line. And this straight line is very indicative of a space charge limited current transfer. So, all right, we think maybe we're not wrong there. And then under negative bias, a dipole can't completely screen the external potential, whereas a parallel plate capacitor would. So we think maybe there's something going on there. So we get a rectifying IV curve, but it's a weird rectifying IV curve that we need to think about and explain. So we do some simulation work. In the simulation we set up here, we're solving the continuity equation, Poisson's equation, and for this device, and we say there's a 500 nanometer device size, or that the change is in 500 nanometers because that's what all the experiments showed. And we say that there's a thermal barrier one direction and space charge limited current the other direction. Okay. And when we include that in the model, we get basically the correct answer. So the thermal barrier we can find by making an Arrhenius plot of the natural log of current versus beta, 1 over temperature. And we get this straight line here, which is a strong indication that there's a thermal process going on. This straight line slope is 0.14 EV, and then the simulation says the thermal barrier is 0.2 EV, and that's pretty remarkable agreement between theory and experiment. And then we can look at the electric field for under positive and negative bias. And what we see here is under negative bias, we have a constant electric field. Well, if you integrate a constant, you're going to get a straight line, right? And that's what we see in the voltage passing. And then in the under positive bias, we see a rapidly changing E field, which if you integrate that again, you get back to the power law. So we think we've included the relevant processes in this model. So in conclusion, we determined the thermal transport limiting mechanisms in alpha and beta indium selenide and showed beta to be a possibly efficient thermoelectric material. And then we developed a scalable laser writing procedure capable of directly defining in-plane phase patterns in two-dimensional indium selenide layers based on local optically activated solid-solid phase transitions. And these phase heterojunctions are sharp and rectifying. I would like to thank WSU, the physics department, for giving me a job for 4 years and buying my dinner. I would like to thank the National Science Foundation for buying Dr. Gu's lab and paying for my dinner the last 2 years I was here. I'd like to thank Clar Scientific for a lot of the devices that we use to make a lot of the images here. I'd like to thank my collaborators, or my committee, Dr. Gu for basically everything, and Matt and Fang for advice along the way. And then I would like to thank my collaborators, especially without whom this wouldn't have happened. So Dr. Feng Zhao and Dr. Xingwen Zhou on the middle third of this presentation, and then Dr. Zhigong Yu and Matthew Gable for the third third of this presentation. And then finally, I would like to thank my friends for putting up with me being an asshole for the last 6 months. And I would like to thank my family for waiting 12 years for me to finish college. Do we have any questions? What's that one?
So the junction width, you were saying that's 500 millimeters wide. Is that something that's intrinsic to the material, like the junction between alpha and beta, or is that something that has to do more with your laser profile?
We don't know. I think it has to do with using approximately a 500 nanometer laser, and that we could get that much smaller using a smaller wavelength laser or an electron beam, but we don't know.
Is there a benefit to having a smaller junction?
You can make smaller devices.
All right.
That's the benefit. Yeah. What's up, Tom?
What do you have a sort of basic explanation for why the thickness of the layer eliminates the boundary effects for the alpha beta?
Because you're farther away from the boundary, right? If you had an infinite crystal that just went on forever and ever, you could never hit the boundary. But if you have a very thin crystal, then it's all boundary. So yeah, you minimize the boundary effect by making a bigger crystal.
So the boundary effect is only relevant at boundary.
Yeah. Yeah. Because that's where the crystal, the structures change, right? Your potential changes between a vacuum and the crystal, and that's what they're bouncing off of. Yeah. So.
Question about the Raman measurements you showed at the beginning.
Mm-hmm.
So like with the vibrations you're studying, are those vibrations like in the plane, so within like an indium layer?
They're more complicated than that. I didn't include the GIF of them,
okay.
But no, it's atoms vibrating relative to each other in one of the 5 layer sheets.
Okay.
Yeah.
So like the different peaks then, are those peaks associated with like a different type of bond, or is it associated with the same type of bond but a different vibration? It's like up and down versus free.
I don't know. Do you know?
Well, there are, so the main peaks, being alpha is a combination. So it's a distribution of 2 two Phonon, I don't remember which.
What's up,
I have
Jeff?
a question, and I want to actually go back to the slide where you discussed the first project, the end. I don't recall what I had, but.
Okay. See if you remember.
Yeah.
Cool.
Which one is the end?
This is the end of the.
Right before you start.
All right. There's some
Click too far.
there's some delay in the clicking, so let's go a little slower. Okay. This is the well. I mean, there's the end, but it's the same slide.
Okay, so I think going here, yeah, okay, so you said alpha phase has semiconductor.
Yeah.
And when you go to beta, it has a different property.
Yeah.
As opposed to the metal.
Yeah, beta phase acts like metal.
Okay,
Yeah.
and its thermal property is like an insulator.
Well, it's very low thermal conductivity. I don't know what the thermal conductivity for metals are offhand, but they're much higher.
I think you stated it was insulator sort of thing.
Yeah, so it behaves as an insulator thermally, not electrically.
But you see electron flow though.
Yeah. So if you heat the electrons in one place, the electrons will move, but the lattice isn't transferring the heat. So there's different ways to transfer the heat, right? There's through the electron flow or through the lattice. And the lattice is, because it's heavier, that's the dominant mechanism in thermal transport generally. But
So my question was, do you know like what was inhibiting that thermal transport of heat?
I mean, I think that's what we show here, right? Is so I don't know just how the computers figured it out, right? Because I can't solve those differential equations on my own. But what we see here is we can explain the low conductivity using the Umklapp scattering, which is it's not going to happen that often because it's a multiple phonon interaction, right? And if that's the dominant mechanism in heat transfer, it's not going to happen very often.
So the explanation to that was the like folding.
Yeah.
Scatter. Okay.
Yeah.
Okay.
What's up,
How
Ethan?
long does it take to build these devices? Like, is that something you have to redo an experiment that's just a pain?
It takes maybe 2 weeks to make one of these junction devices, start to finish, and then you can start testing it. But if you mess up along the way, you have nothing. We're working on the next project will be to CVD grow it, which would be much quicker, and then to do patterning on CVD grown materials instead. But I probably won't be here to do that. So maybe if you don't graduate, you can watch Cassie give that talk. What's up, Jason?
Yeah, actually, I have a good question. So in the beginning, you mentioned the figure of merit of one and how that was really good, and that's like industry devices. So I guess what is the figure? Like, what does that actually mean?
So it's the thermoelectric figure of merit, and it's defined as this unitless quantity that's the ratio of a bunch of things, right? And they take the ratio to make it unitless so you can compare, a whole bunch of different kinds of devices. And I don't know the specifics of how you do it, but it's a count of how many electrons you get per heat difference across the material. Yeah. And then, a figure of merit of 1 is about what is industrially used. And then, 2 is the world record. And that was achieved with a device like this.
And so, like, would 0 be like still a device, or would that be like
Zero would be like a pure insulator or a vacuum, right? Like the temperature difference across a vacuum is meaningless because there's nothing there to carry the temperature. And then an ideal insulator would never conduct an electron, no matter how much of a temperature difference there was. So the figure of merit is a way to take those two extremes and crunch them into one number. Yeah. Cool. Anything else? All right.
Wow, not.
Now, you want me to leave my family watching this part, right?